Day 123. Bent mirrors may be concave or convex. Here's a picture of a convex mirror. You're standing there and the middle of the mirror bows out towards you. Please stop talking. And so this is called a convex mirror. It will make you look smaller. And then we have another kind. You can imagine already what that might be like. If this is one kind, the other kind will be what? Think about it for a second.
Why, thank you.
It'll be bowing away from you in the middle. This is called concave. Sometimes it makes you look bigger, sometimes it makes you look smaller, depending upon where you are standing and how curved it is. Though you need to know the difference between these. You need to be able to identify this is concave, this is convex. And it's kind of hard because these words are so similar to each other. C-O-N at the beginning of both. The way that I remember it is that I think about a really extremely bent surface like the concave, but really concave. And look, it's like a cave with a bear in it. There are the bears hibernating. Okay? So concave is the shape of a cave if you can crawl into it. Number 2, if a curved mirror were extended to make a full sphere, the center is called the center of curvature. Center of curvature. So this convex mirror could be extended and it would make a sphere with the center, we're going to label that as C. This one, it could be extended to make a full circle and we'll label the center C. This point is not used much in our work, but it is a reference point that is used to make predictions about the type of images that are made. If you're on one side or the other, different kinds of images are made, and we'll explain that as we go along. Light rays that are parallel to the principal axis of a concave mirror are reflected through a point called the focal point. So we have a couple different words there that we need to define. First of all is the idea of principal axis, this thing right here. The principal axis is the line that goes through the center of curvature and through the center of the mirror. So here I have curved mirror. Here's the center of curvature. If I made this sphere a complete circle, that center would be in the middle. Okay, now let's imagine some parallel rays. This line right here is the principal axis. Or oftentimes we'll just simply call it the axis. Here we have one ray that is parallel to the axis. It's coming, it's going to hit the mirror. It's going to get focused downwards. It's going to be bent down like that. Now, the way that it's bent, let me draw another line. From the C to the mirror. That's the center of curvature, the center of the circle to the circle itself. What do we call a line that goes from the center of the circle to the circle itself? Radius. The radius is always perpendicular to the surface there. Remember, perhaps you're talking about tangents in geometry class, and the radius is always perpendicular to the tangent at that point. Okay, so here we have the incoming angle and the reflected angle. Those are equal. So by this path, it's going to get bent down through that spot on the axis. The opposite would also happen. If I had a ray coming up through this spot, it hit the mirror, and by equal angles, it would go parallel. These are two-way streets, so to speak. Okay, let's look at another line. Let's look at one down here. Where's my other pen? Here it is. Okay, so let's get one a little bit closer. And it's going to go across. And by equal angles, it's going to get reflected like this. it ends up crossing the axis at the same point. And let's do one more line. Let's do it really close to the axis. This one is going to have a different normal, a different radius that hits the mirror. So it's going to reflect at different angles. But the angle that it reflects at is going to send it through, guess what? The exact same point on the axis right there. This point is exactly halfway between the center of curvature and the mirror itself. This point is called the focal point. We're going to label that with an F. That's the spot. The point is the focal point. The distance from the focal point to the mirror is going to be called the focal length. With each one of these paths, whether it be the blue or the black or the red, remember it works both ways. The ray of light coming through the focal point hitting the mirror will be bounced parallel. Okay. Next page. I don't have the 5-beam laser thing working. Let's go on to the video.
A solar energy.
Sorry, that's the wrong one. Why didn't it come up? Here it is. Okay, so students, a teenager, got one of these satellite dishes that's normally used for television, and they covered it with 5,800 tiny little mirrors. Took a while, but it looks pretty. That is not at the focal point. A lot of light is shining here, but not all of the mirrors here are reflecting onto the spot. He's going to move it, and instantly it's going to burst into flames. For those of you who have tried to build fires, you know that it's hard to get a 2x4 to burn. You have to get a lot of kindling underneath it and a lot of papers or bark or whatever, and then after a while, then yes, the 2x4 will start to burn. But see how quickly this thing starts flaming. Notice here in the smoke we can see the rays coming in. Normally the sun rays are all parallel, coming down at the same angle, but then they get bent by the curve of the dish here, and you can see coming in. And so all of those different mirrors are focused in this one spot. Notice he has welder glasses on. Not only is it 5,000 times hotter at that spot, it's also 5,000 times brighter. So if you looked at this, not on a computer screen, but in real life, it would be so bright it would probably ruin your retina. And so you'd be blind for a large portion of your vision. So if you do something like this, hey, It looks like a great little project, but realize the danger that you're in. So, two things. Number one, welder's goggles so that you don't burn your retina. And obviously you don't put your hand where the bright spot of sunlight is. If it bursts a 2x4 into flames within a second, it's going to do severe damage to your hand in less than that. And you can talk to the teacher across the hall about what it's like to spend the night in the hospital because of a burned hand. Not only does it start wood on fire, but it can evaporate metal. Think to yourself, how can mud burn? Well, there's grass and sticks and leaves and other kinds of organic material in there that can burn. How can pieces of rock pop off because of sunlight? Casey?
Because the rock's more brittle and because there's enough energy that it will crack.
Okay, it's brittle, that's part of it. The outside is going to heat up faster than the inside. What happens to objects when they heat up mostly, usually? Expand is the word. So the outside is expanding, but the inside is not. So that causes things to build up stress and pop off. Okay, that's interesting. I bought some dishes, some satellite dishes at a garage sale, and in the back I tried to coat it not with mirrors because I'm not that ambitious, but I coated it with aluminum foil, and I was able to make some toast. It took a little while, it took about 5-10 minutes, but I made toast. It was yummy. Okay, next. How do whisper dishes work? In normal talking, you only hear the sound waves directed straight at your ear. So here's the person talking, here you're listening. Sound waves go in all sorts of directions and all sorts of elevations. You do not hear this because it does not hit your ear, it goes above your head. You do not hear this sound wave because it goes below your chin, not your ear. You only hear this sound wave that goes directly to your ear. Now there might be a couple others that bounce off of the floor, but it only is the ones that hit your ear. A whisper dish is a giant thing like what I have here in the room. You'll usually find them in science museums. Some playgrounds have them, but they're curved surfaces where you can whisper and hear each other from great distances. With whisper dishes, the speaker puts their mouth at a focal point. In this way, sound waves go in all directions. They hit the dish and get reflected parallel to the axis. So here's a speaker. Ones go up, go parallel. This way, parallel. Down here, parallel. They all end up going parallel off the dish. This beam hits the other dish and gets reflected to the focal point where the person has their ear. So this parallel line reflects to their ear. This parallel line reflects to their ear, etc., etc. So instead of hearing just one sound wave, you end up hearing 4, or however many you draw in there. This is the same way that satellite dishes work. With a satellite dish, you have the curve, you have a stick, and then you have this bumpy thing. So stuff reflects off of the dish and ends up going on this side of the bumpy thing. Well, you could have taken that bumpy thing and just simply held it up with the flat side not to the dish, but simply pointed towards the satellite and get a reception. But you're only getting, 4 inches, 3 inches worth of satellite signal. It's not that sensitive. It's not going to read it well. However, with this, you get the satellite signal coming down, straight down at the dish, and all of these end up hitting the bottom of the sensor. And so now you have 3 feet worth of signal instead of 3 inches. And so it's concentrated, so to speak, amplified, and you can read it much better. You may have seen the dishes that the camera people have for television when they're broadcasting a football game, and you can hear the grunts and the groans so much better. Familiar with that idea, perhaps? Satellite dishes do the same thing with radio waves. The sensors are actually not in the dish, but the end of the pole at the focal point. So this little bump here, that sensor for the satellite dish, is at the focal point. Okay, how do you draw a ray diagram to find the images of a concave mirror? All of these curved surfaces that we've looked at so far are concaves. Your homework problems in this class will only have objects whose bottoms are on the axis. This simplifies things. Even in college, that's how they always had the examples. For these, you only need to draw 2 rays from the top of the object. Makes things so much easier. Others could be drawn, but it would not improve your answer. Step number 1. Lines parallel to the axis are reflected through the focal point. And once you draw that reflection, you can scribble out the incoming ray. Step number 2, lines that head towards the mirror from the focal point end up reflecting parallel to the axis. Julian, are you sure that you want to spend your time that way? Well, again, once you draw the reflected parallel ray, you're going to erase the incoming ray. The reason why we crisscross out or scribble out the incoming rays is that we're going to look for the image location where our reflected rays crisscross. So you don't want to get the wrong crisscross, and some people get confused by it. The base of the image, it says here object, let's do image. The base of the image is always on the axis, and so that simplifies things a little bit. We look for the crisscross and we look for the axis. We draw our image between the two. If the crisscross is above the axis, the image is right side up. If the crisscross is below the axis, the image is upside down. But you always have the bottom of the image on the axis itself. If that sounds kind of confusing, you'll understand in a moment here when we draw this next problem. Okay, we're going to draw the rays, we're going to figure out where the image is, and then we're going to label it in 3 different ways. Okay, step number 1, we're going to need rulers or some kind of a straight edge so you can draw this accurately. So let me get you some rulers. Billy, pass it down. Take one, pass it down. Take one, pass it down. We got 3 of them. Yeah, we got 3 of them.
Magic. Oh, that one guy's great.
Okay, here we go. First step, draw a ray from the top of the arrow object parallel to the axis until it hits the mirror. If I was to draw the normal and the equal angles, we would see that that would be reflected through this focal point right here. The point that's closest to the mirror is always the focal point. The farther one is always the center. Once you draw this reflected ray, please scribble out the incoming ray. And then we're going to draw the ray that goes from the focal point to the mirror. And that's going to reflect parallel. If I was to be out here, looking at these two rays, thinking to myself, where did those rays originate? My first thought would be this spot right here. So that is the image of the arrow tip. Now, light from the base is just going to go down the axis and bounce straight back. So the base, the image of the base is going to be on the axis itself. So I have the tip here, the base there. This arrow is going to be appearing to be upside down. There's your image. Now, a lot of students do it wrong, and they say, oh, look, there's the crisscross, and so my image is going to be like that. No, that's wrong. Wrong. Do not do that. Whatever the base of the object is, here the flat end, is going to have its image over here, flat end, on the axis. Okay, now, this image, you can obviously see that it is less tall, it is shorter than the object itself. So we could call it shrunk, or we can call it reduced. Either way. On multiple choice, you might see either one of those. The object is an arrow pointing up, the image is an arrow pointing down, so that means it is flipped, or in other words, inverted. You might see the phrase upside down. And there's another way that we can label this. Line number 7. These images are called real. So let's put the word real up here. Because the light rays really do travel through that spot. I could put a piece of paper here and the image would be glowing on the paper. This is how movie theaters work. Well, that's kind of image made by a movie theater. They use lenses, they don't use mirrors. But the same sort of idea is happening here, sort of. These images are always upside down. Real images are always upside down. And they are always in front of the mirror. With our flat mirrors last week, we saw that the image location was actually behind the mirror. If you stand 3 feet in front of a mirror, the image is 3 feet behind the mirror. Well, here the image is in front. And there's not a simple relationship between how far away the object is here and how far away the image is here. There is a relationship, there is an equation, we will learn it later on, it's just not easy. Okay, so, Adler Planetarium story. This is one of my favorite stories to tell. For some telescopes, they work to magnify the images of the planets and things by a curved mirror like this. And so at the Adler Planetarium one day when I was visiting just on my own for fun, I saw that they had a 4-foot concave mirror. Oh, that's kind of cool. And then I realized, hey, I could have a hologram of my head. I could have this real image floating in space. So let me try. So I finagled myself to be in the right location. I had to find a chair in order to stand on to get in the right position. And there, right about arm's length away, was an upside down, slightly reduced version of my head. Not much smaller, but maybe 3/4 of the size. And to amplify the appearance, I could put my hand in space right under where my image was in space. So it really looked like I was holding my decapitated head. Very cool. And then to amplify that feeling, I could turn my head and turn my hand at the same time, and that would even more make it look like I was holding my own decapitated head. Very cool. And then I poked myself in the eye, and I felt it. I'm not kidding. I poked the image of my eyeball, and I felt something in my eye. And I thought, what in the world's going on here? This is hocus pocus, this is black magic, this is voodoo. No, it's not. I tried to think, what's going on? Well, remember all the different lines here. We have red and blue. I could draw green and black and purple and all sorts of other rays hitting the mirror, and they would all go through the same focal point. They'd all end up going to this same spot in space that I see as an image of my eyeball. All of the rays, coming off my eye in all different directions, bouncing off the mirror, going to that one spot. When I put my finger there, the opposite is also true. All the light rays that are hitting my finger from all different angles are going off, hitting the mirror, and going to my eye. My eye is trying to focus this giant image of a giant finger. When your eye focuses on an object, there's actually muscles in your eye stretching your lens. So when I poked myself, I could feel the muscles in my eyeball reacting, trying to move a little bit. It was very cool. I wish I could get that kind of mirror. I would take you guys down to the museum just to see that if I could, but unfortunately they've taken it off the display. This one, I like that story. Okay, here we go. Next. We've now moved the object a little bit closer to the mirror. How is the image going to change? Think about that for a second. Do you think it's going to be closer to the mirror or farther away? Do you think it's going to get bigger or do you think it's going to get smaller? Go ahead and write down your prediction right now. Thinking about how these rays work and the angles, think about how these angles are going to change as you get closer to the mirror. How will the crisscross change? Okay, let's see how it goes. First step, draw the parallel ray. Did that change at all compared to the top picture? No, didn't change at all. Well, it's a little bit shorter, but it's no farther away from the axis than before. It hits the same spot in the mirror as before. Draw the reflected ray through the focal point. Did that reflected ray change at all compared to the top? Nope. It's the same angle. It's going down through the same focal point from the same spot. Everything's the same. Okay, once you've drawn the reflected ray, scribble out the incoming ray. Next, draw the ray from the top through the focal point to the mirror. Is that ray any different? Yes, it is a little bit different. It's a little bit steeper, right? it's going to hit the mirror a little bit lower. Draw the reflected ray. Scribble out the incoming ray. Is that parallel ray any different than before? Yeah, a little bit. This one's a little bit closer to the axis than this one. We're now lower. How is that going to change our image? It's going to be a little bit bigger. And it's going to crisscross here a little bit to the left. Here, the image is closer to the focal point than the center. Now, it's closer to the center point than the focal point. Notice it's a little bit taller, the image. Okay, now, I didn't emphasize this before. I need to emphasize it now. And I didn't scribble out the reflected ray. Remember that the crisscross is where the image is. And if you don't scribble out the incoming ray, some people have said, "Oh man, I have two crisscrosses here. Which one works?" So that's why I have you do that. It's not of the utmost importance. You can do the problem without the scribbling out, but that's why I do it. Okay, so this, we have the image is a little bit bigger than before, but it's still smaller than the object. So we still call this reduced. Smaller, shrunk. It is still pointing down while the object is pointing up, so it is still inverted. Light rays are really truly passing through this spot, and so it is still a real image. The location is a little bit farther away though, farther from the mirror. Okay, here, the next one, we actually have the object right at the center of curvature. This is going to result in something slightly particular. Go ahead and you draw it. Draw the rays just like we did before. And let's see what's special about this location. Compare your first line with mine. Compare your second ray with mine. Now we have two crisscrosses, so I scribble out the incoming ray, and we can see that that's not the crisscross we're talking about. It's this one down here. So there's my image. If the object is at the center of curvature, the image is also at the center of curvature. And notice that the heights are going to be the same. So this is not reduced, it is not magnified, it is the same. Same size. It is still inverted. Would I still call this real? Do the light rays really travel through this spot? Yeah, they do. So it is still real. Okay, now, as the object is brought even more close, what do you think is going to happen to the image? Make your prediction now, because that's what we're going to be drawing. So here's our first line, parallel. It reflects through the focal point. That is always the same. It hits the mirror at the same height. It goes through the same focal length at the same angle. That doesn't change. Sam. The blue line. The second ray is going to go through the focal point just as before. Notice the difference now. Scribble out the incoming rays. And the crisscross is way over here, way down there. So the image is really big. We call that magnified. Magnified. You might also see the word enlarged. It is still inverted or upside down. It is still real. Marco.
At what point do we consider it enlarged? When it's just bigger than normal?
Yes. Yep. So when the object is right at the center of curvature, the image will be the exact same size. Once you get a smidgen closer to the mirror, then the object is going to be bigger. The image is going to be bigger than the object. Okay, the next one. Now we are closer to the mirror than the focal length. At the focal length itself, we cannot have an image because you'd have a line from the tip of the arrow straight down to the focal point, and then it would miss the mirror altogether. There is no image. But here, when it's closer, we have an image. So the first line is exactly the same. It is still parallel to the axis. It still bounces back to the focal point. The second line, though, we cannot have a line go from the top of the object to the focal point and then go on and hit the mirror. It's going in the wrong way. So I need to direct your attention to this previous page, and I worded things very carefully. The second step is lines that head towards the mirror from the focal point. From the focal point direction is what I was meaning. So we need to draw towards the mirror from the direction of the focal point. Like that. This blue line here is going to hit the mirror, and it's coming from the direction of the focal point. The geometry is the exact same whether it actually went through the focal point or not. Geometry is still going to tell us that it's going to go parallel to the axis. So as I am sitting out here looking at these rays, my younger days when I had lots of hair, when I'm looking at these two rays, where would I say that they came from? Where's the one spot in space where they appear to have originated? Well, I need to extend these lines. I draw dotted lines because light rays are not actually traveling back there. But it just looks like they did. It appears that these two rays came from that spot. So that is the image of the point, the arrow point. The object's base is on the axis, so the image is going to have its base on the axis. So it's going to look like this. It's right side up. The crisscross is above the axis, and so the image is right side up. And it is clearly enlarged. It is magnified. Magnified or enlarged. It is right side up. Do light rays really travel through that point in space? Nope. It just looks that way. It appears. It's imaginary. So, thinking about the imaginary world of computer goggles and things like that, we use the word virtual reality for those. They don't really exist. It's just on the screen. So here we have virtual images. It's not a real image. It's a virtual image. These images are always right side up type of image. It is virtual. Or What was I thinking when I put those blanks? I'm not sure. But they are always behind the mirror. And they are always right side up. As we get closer and closer to the mirror, how do you think the image is going to change? Imagine how these lines are going to either stay the same or change, and how will those affect the image, both in location and size? Think about it for a second. If you think the image is going to get bigger, put your finger up like this to your neighbors. If you think it's going to get smaller, point it down. Let's see if you agree with your neighbors. Go ahead, let's see. Make a commitment here. Don't feel bad if you're wrong. Will the image get closer, a smaller distance, or will it get farther away from the mirror, a bigger distance? Put your fingers up and down for that. And now let's see if you're right. The first line is going to be parallel, bouncing to the focal point. That is the exact same as before. It's just that this section is a little bit shorter. The next line is the one that's different. This blue line is going to be a little bit more shallow, not as steep as up here. And so it's going to hit the mirror at a lower point, and it's going to reflect as a parallel ray that's closer to the principal axis. So with that in mind, how is that going to change the size of the image? Was your prediction correct? Now, our next thing is going to be extending these lines back. Think about extending them back. Are they going to crisscross closer to the mirror or farther away from the mirror compared to this up here? Was your prediction then correct? They're going to crisscross closer to the mirror. So the image gets smaller and closer as you move towards the mirror. Next page. Hold out the double-sided mirrors. Okay, so I have small mirrors here. Where are they? Here they are. You're going to look at the side. That looks like the inside of a bowl. The outside looks like the outside of a bowl. Okay, inside of the bowl. You're going to hold it at arm's length. And you're going to see that you have a small face, and it's upside down. That image is actually located somewhere in space between you and the mirror. And then, okay, so your image is upside down. And small, reduced. As you get closer and closer, the image is going to get bigger and bigger. Can't see it. Sorry. Thank you. As you get closer, there's a point where there's no image at all. That's at the focal point. As you get closer from that, the image flips, and it's big. It's magnified when you get it up close like this. So, folks with makeup mirrors, this is the kind of thing that you use to put on your mascara and eyelash stuff. When you get up close, it's magnified, so you can see that kind of detailed work. The new image is initially large, and as you get closer, the image gets smaller. Okay, and that's as far as we're going to be able to get. This flying saucer hologram is not critical to the lesson, so we're going to stop the video here. The bottom here, we have another use for this stuff. We had the teenager with the 5000 mirror. Here is a survival fire starter. Same principle though. You put a little bit of paper here or kindling, a little piece of birch tree bark, whatever, and focus this or point it towards the sun, and it'll start that on fire. Okay, now I can stop it.